In this video, I would like to talk about the rules for determining the hybridization of a given atom. And rule number one here says that the number of hybrid orbitals on an atom is computed by adding the number of sigma bonds and the number of lone pairs on that atom. And once you determine that number, then you can predict the hybridization. So if you determine that the number of hybrid orbitals is 2, it's going to be sp hybridization. It's going to have a linear geometry, and the approximate bond angle will be 180 degrees. If you determine that it should be 3 hybrid orbitals, then it's sp2 hybridized, trigonal planar, and 120 degrees. And finally, if there are 4 hybrid orbitals, that means that they will be sp3 hybridized, tetrahedral geometry, and 109.5 degrees. Now, rule number 2 says that you want to use the hybridization in geometry that give the greatest possible separation of the calculated number of bonds and lone pairs. And the idea behind this is that is related to electron repulsion theory, in that the energy of the system is minimized by maximizing the bond angle between both lone pairs and bonding pairs. So let's look at ammonia, for example. If we look at ammonia, we see that there are 3 hydrogens bonded to it, and there's 1 lone pair. So that means 3 sigma bonds and 1 lone pair. Therefore, there should be 4 hybrid orbitals. If I have 4 hybrid orbitals, therefore it's sp3 hybridized, tetrahedral geometry will give the greatest separation of those sigma bonds in the lone pair, and you're going to see something that is close to 109.5 degrees. Now, if you look at ammonia, it's not exactly 109.5 degrees, it's because that molecule is not perfectly symmetric, and in fact, the lone pair of electrons, a non-bonding pair, actually repels the bonding pairs and kind of squeezes those bond angles down a little bit to 107.3 degrees. So we can see that rule number 1 and 2 allow us to determine the hybridization. Here's another important rule. If 2 or 3 pairs of electrons form a multiple bond between 2 atoms, the first bond is going to be a sigma bond, and that's going to be formed by a hybrid orbital. For example, the overlap of sp orbitals or sp2 orbitals, and that's going to give us a sigma bond. The second bond in that multiple bond is going to be a pi bond, and that's going to consist of 2 lobes above and below the sigma bond formed by the overlap of 2 unhybridized p orbitals. For example, we saw this in acetylene and ethylene, which had a triple bond and a double bond respectively. If there's a third bond, for example, in acetylene, that's going to also form a pi bond, and it's going to be perpendicular to the first pi bond, as we saw. So let's take an example of formaldehyde. Now, formaldehyde has a carbon double bond oxygen, and it has 2 hydrogens bonded to that carbon. So let's take a look at carbon. What should be the hybridization of that carbon? How many sigma bonds are there to that carbon? Well, if we look at that, we see there's a double bond, but only one of those bonds is a sigma bond. The bond with the hydrogens are both sigma bonds, so there's 3 sigma bonds. There's no lone pairs on that carbon. Therefore, there should be 3 hybrid orbitals, and that means, going back to the previous table, that the hybridization should be sp2 with trigonal planar geometry. And that's going to give the greatest separation of those sigma bonds. So we predict then that that's going to be an sp2 carbon right there. And remember that a double bond, you're going to have the first one is going to be sigma, and the second one will be a pi bond. What about the oxygen? We can apply these rules to other atoms besides carbon. So if I take a look at the oxygen here, how many sigma bonds are there to the oxygen? Well, there's just 1. There's 2 lone pairs. You can see that. And that adds to 3. Therefore, there should be 3 hybrid orbitals for oxygen. And that means that, in fact, it should be sp2 hybridized as well. and that's going to have trigonal geometry to give that separation of the sigma bonds and the lone pairs. And rule number 3 applies again. The double bond, there's just one sigma and there's one pi bond. So let's take a look at the orbital picture of formaldehyde. And first of all, let's start out with our 2 hydrogens, which both have a 1s. And we are going to bond those hydrogens to the carbon, because they're both bonded to the carbon. And the carbon we know is sp2 hybridized. And so we have a trigonal planar arrangement of the hybrid orbitals, 120 degrees apart. sp2, 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 they're in the plane here. And here is a p orbital, since that's left over on an sp2 hybrid, there's a p sub x. And then we also have an oxygen that's involved in the bonding, and that's also sp2 hybridized. Again, sp2 hybrids, trigonal planar with a perpendicular p orbital that's perpendicular to the sp2 orbitals. So then how is this going to bond? Let's talk about the carbon-oxygen double bond. The carbon is going to donate an sp2. Oxygen donates the same. Those will overlap to give us that sigma bond. And then the px's will overlap to give us the pi bond, both above and below. And we're going to therefore have a double bond between the carbon and the oxygen. Where do the hydrogens come in? They come in and overlap with the sp2s of the carbon. And those are going to be both sigma bonds, as you can see. And then what about the lone pairs? What are they occupying? Well, they're occupying the sp2 orbitals here. And so there's a lone pair out this direction, and there's a lone pair out this direction. And they're localized lone pairs here with a pi bond formed between the carbon and the oxygen. So we see a trigonal planar molecule, all atoms in the same plane, because this is a sp2 hybridized system. And you can see that it gives you this kind of a Lewis structure here, with this hydrogen coming out towards you and that hydrogen going away.